So 5.6 related rates. Obviously, we've been doing this already, but for the book problems here, it says assume all variables are differentiable functions of t, and basically in each problem they're going to tell us what to do. But it says, like with number 2, the radius r and surface area s of a sphere are related by the equation s equals 4 pi r squared. Write an equation that relates ds dt to dr dt. So essentially we're just basically taking the derivative of it. They're just having us do everything except for the actual solving part. So we'd have ds dt is equal to 8 pi r dr dt. And that's all like with those ones that we have to do as far as that goes. For kind of a two-part problem here, it says the power P in watts of an electrical circuit is related to the circuit's resistance R in ohms and current I in amps by the equation P equals RI squared. And then first it says, how is dP dt related to dr dt and di dt? And then the second part we'll do in a second says, how is dr dt related to di dt if P is constant? So we'll look at that in just a second. So that means basically I need to take the derivative, but I've got a chain rule, so I'm going to have dP dt is equal to the derivative of the first, so dr dt times the second I squared, plus the first r times the derivative of the second would be 2i. I want to put the 2 in front of the r, so 2i di dt. And there's really nothing else I can do with this other than pretty much if I wanted to, reorder the letters or whatever, but I don't need to do that. So I would just leave that one there. So then part B says, how does dr dt relate to di dt if P is constant? So if P is constant, the only thing that's really changing from my original equation is that dP dt is just going to be 0 instead, because I wouldn't have ever had a dP dt. So we would have 0 equals I squared dr dt plus 2ri di dt. And then it wants dr dt related to this other stuff, so that means I'm going to need to move this piece over. So I'm going to have negative I squared dr dt is equal to 2 ri di dt. Then I need to divide by the negative I squared, so dr dt is going to be equal to negative 2. The I on top cancels with the squared part of the bottom, so 2r over I di dt. So just manipulations of the formula depending on what they would be asking you for given information.
The 0 again?
They told me that P is constant, so that basically in this original equation P equals RI squared. If P is constant, it's like the one where we were looking at the what was it? The ladder, like the height of the ladder wasn't changing. So the way we did that, where we were like, okay, well that's just gonna, like, when you take the derivative, it's going to 0. So I just took this equation here and I just swapped that out with a 0 because if it's constant, it can't be changing, so I can't have a derivative of it. we'll get into a couple here that actually have stuff we're solving. Number 8, heating a plate. When a circular plate of metal is heated in an oven, its radius increases at a rate of 0.01 centimeters per second. At what rate is the plate's area increasing when radius is 50 centimeters? All right, so I know that I'm dealing with a circular plate and I'm dealing with area, so I would say A equals pi r squared is going to be my formula. So then that tells me, obviously, I'm dealing with A and R as my variables, so I'm going to set up my little thing on the side here. So they tell me that the radius is increasing at a rate of 0.01 centimeters per second, so that's my dr dt. The radius is 50 centimeters, so that's r. Area, because I know ultimately I'm taking the derivative, I don't really need that. I can find it if I am so inclined, but I'm just going to put a slash there. And then dA dt is obviously what I'm solving for, because that's the area, the rate the area is increasing at. So take the derivative, we get dA dt is equal to 2 pi r dr dt. And then obviously we can plug this stuff in. So we've got 2 pi times 50 times 0.01. And do they leave? Where's the answer? Oh, well, 100 and 0.01 basically just cancel out, I think. Helps if I multiply, yeah. So basically 2 times 50 is 100, and then times 0.01, that just is 1. So then this ends up being pi, and then because it's area, centimeter squared per second. So all I have to do on one like that. Let's see, 12. Growing a raindrop. Suppose that a droplet of mist is a perfect sphere and that through condensation the droplet picks up moisture at a rate proportional to its surface area. Show that under the circumstances the droplet's radius increases at constant rate. So I'm really not finding anything in this one, or like I'm not solving for a particular value. I'm just showing how this one would work, essentially. And so I've got, you know, a spherical water droplet. So looking at the formula for this one, I know I'm going to need basically V equals 4/3 pi r cubed. And I'm looking at ultimately trying to find the droplet's radius. So that would be dr dt is what I'm going to be trying to find. And then we've also got volume and the change of volume. So this is what I'm solving for here. So they tell me that the droplet picks up moisture at a rate proportional to its surface area. So the other thing then that I would need is the formula for surface area, where that is S equals 4 pi r squared. Yeah, I think that's right. Pretty sure that's the right formula. So then, let's see, what else does it say? Perfect sphere, and that through condensation the droplet picks up moisture at a rate proportional to its surface area. Show that under these circumstances the droplet's radius increases at constant rate. All right, so I would say go ahead and find the derivative of this function over here. So dv dt is equal to 4 pi r squared dr dt. And then obviously we said that the surface area formula is, 4 pi r squared. So I noticed right away that that looks like volume is basically surface area times the rate of change of the radius. And it says that it's happening at basically a constant rate. And so I'm going to say let K be the constant rate essentially like with the surface area. So that would mean that we have dv dt equals K times the 4 pi r squared part of that. If I set the two things that I had equal to each other, so this basically the K times the 4 pi r squared and this 4 pi r squared dr dt, because both of those things are equal to dv dt, then I can solve it down and basically prove what I'm trying to show. So 4 pi r squared dr dt equals K times 4 pi r squared. Divide, and I get dr dt equals K. And so droplet's radius increases at a constant rate. Then that makes sense. It's a weird one. I wouldn't be as worried about it. Yeah.
Like, what in the world was the point of doing that? You just pretty much said drdt equals drdt.
It's just showing that, like, you can say something is proportional if it's, like, constant, basically, is all it's doing for you. You're not really solving anything. I'm not inclined to give you one like that. I just kind of wanted you to see it in case, like, you ever get something of that. But they're more inclined to actually ask you to solve one of these problems rather than, like, just show this. But, yeah. Not, like, the best problem in the world, but... Let's see, something more realistic maybe. Flying a kite. Sounds like a good option. I don't even know what the name is. Some girl flies a kite at a height of 300 feet. The wind carrying the kite horizontally away at a rate of 25 feet per second. How fast must she let out the string when the kite is 500 feet away from her? So we've got the girl. The kite is at a height of 300 feet. So I'm just not writing out the whole problem, I'm just writing out the key information. And then it says that basically the kite's over here. The wind carrying the kite horizontally away at a rate of 25 feet per second. How fast must she let out the string when the kite is 500 feet away from her? So this value here, the hypotenuse value, is 500 feet. So make sure I have everything. Oh, and then the rate of 25 feet per second. So basically we've got, I'm just going to use D for distance. So the distance of the kite is 500 feet away. And ultimately we're solving for then dd dt, which is the rate she has to let the kite out at to do that. H, which is the distance basically from here to here, we have to solve for. And then dh dt, which is the rate that it's moving horizontally, was given to us. It's 25 feet per second. So this other value here is only really going to be helpful. Like, I don't really need it for anything other than finding what h is equal to, because essentially, well, I mean, I'm going to use it, but like it's just a value that's getting plugged in. Like, that's not changing the height of the kite. Nothing's happening to that. So h is equal to the square root of 500 squared minus 300 squared. And this is essentially the same as like a 3, 4, 5 Pythagorean triple. It's just with 100, so that would be 400. And so similarly, like, I don't necessarily need the fact that the kite is 500 feet away from her other than to solve this value and find what h is, because I'm going to be taking the derivative of the equation, so it's going to be going away. But we've got d equals the square root of basically these two sides added together, so 300 squared plus h squared, which I would rewrite this as like in parentheses, the way we do this, where we're like 300 squared plus h squared, whoops, to the 1/2, so I can take the derivative. So we'd have dd dt, should have chosen a different letter, that's a weird one, is equal to 1/2 times 300 squared plus h squared to the negative 1/2, and then the derivative of the inside times 2h dh dt. Yeah. Implicit in a chain rule. Yeah, that's right. Okay. So then at this point, I would probably, I mean, you could either go ahead and plug things in. Since I know I'm solving for dd dt, I can go ahead and plug all my numbers in and start solving, or I can like move this stuff around and make it look pretty first. Do you care?
No.
Okay. So we're just going to say dd dt is equal to, as I go, I'll like put the stuff where it goes. But on the top, we would have 2 times h is 400, and then dh dt is 25. On the bottom, we would have the 2 and then the square root of this stuff. So the square root of 300 squared plus 400 squared. So that means on top, we've got 800 times 25. Well, actually, let's just do it this way. 800, and then I'm going to do it times 25 because I can cancel stuff out. Over 2 times, that's 500. Well, the zeros and the 800 and the 500 cancel. And then basically I've got 200 over 10, just 20 feet per second. So that would be my d/dt. Obviously, you could also just plug it into a calculator and get the value without having to, but I saw that they would cancel nicely, so I just went for it. See if there's anything else here that we need to hit. I think that's probably pretty good with as far as that. Do you have any questions about those? Then I'll give you a few problems out of the book. I think I said this yesterday, but if we are in school on Monday, you'll have like Monday to do them. If we're not in school on Monday, just like hit the problems then. And then tentatively, we're planning on quiz on Wednesday, but if something happens with school being out more than that or whatever, we may adjust it. We'll see where, obviously it's just you, so you can kind of tell me if you feel like you need more time, if you're ready, whatever. We'll play it by ear. I was like, I'm not making any lesson plans for next week past like Monday.
Yeah.
Because I'll have to redo them all. Because if I make a plan, we're going to be out of school for the whole week. Like, that just would be my luck. So in the book, let's go with 1, 5, 11, 17, which will be similar to the cone problem with either the water or the one with the sand. I can't remember right off the top of my head which way that one works out. And then 19 as well, which is a ladder sliding problem. So it'll be similar to the one that we did, obviously with the ladder sliding down the wall. Did you finish the ones in the packet?
Yeah.
Okay. I'm going to stop